All right, thank you to the organizers for the invitation. This is actually my first time in IPAM, and I have really enjoyed the format of the event. And I hope that we can continue coming here for other workshops. So today I'm going to talk about a project that it is still ongoing. It is not under archive yet. It is with joint work with Hailong Dao, Ezra Miller, Chris O'Neill, and Kevin Woods. And hopefully by this summer, you're going to find the paper on the archive. All right, so let me start with this rather bold takeaway that I want to convey with this talk, which is the fact that if you want to study the growth behavior of a family of objects in algebra, combinatorics, or geometry, then if you can find a finite condition satisfied by the whole family together, then you can kind of predict how it is going to grow. Okay? So for instance, there are a couple of families that we have already seen several times in this event. As you know, we have the Hilbert polynomial of a standard graded algebra. So this is an algebra that is generated by the elements in degree 1. In particular, it's Noetherian, and the 0 degree piece is a field. Then we have the so-called Hilbert polynomial that it measures for n big enough the dimension of a vector space of the nth graded piece. Okay? And the way you prove this is because of a finiteness condition of Noetherianness, right? So because the algebra is Noetherian, you have a finite free resolution. Then from the free resolution, you have the generating function for the Hilbert function of the ring itself. And because of the finiteness of the resolution, you can combine them together to get the polynomial, right? Then you also have the Erhard polynomial. And the finiteness condition here is, well, you have a bounded object, but it's not just bounded, right? You can describe it by finally many linear inequalities, which are the ones satisfied by the facets. And a little less obvious and maybe out of topic with respect to the other two, but I thought it was a good idea to put it here is the snapper polynomial. If you consider an invertible sheaf in a projective scheme, then the Euler characteristic of the powers of the sheaf also behave like a polynomial. And you might think, well, the finiteness condition here might be because locally you have this rank 1 isomorphism that allows you to predict how this thing is going to grow. Right? So if the words that I highlighted on the first two parts, standard and lattice, are removed, you still get something. But you don't get polynomials anymore, but you get a quasi-polynomial. Okay? If you have never seen this, it might seem a little artificial at the beginning, but it's going to show a lot in this talk. So by the end, you're not going to find it that artificial, I hope. So a function is quasi-polynomial if instead of just one polynomial, what you have is finally many polynomials that agree with your function periodically. Okay? So you can write that as there exists P1 to P pi such that Pn coincide with Pi for any n congruent to 1 mod pi. Okay? All right. Now, these are by no means the only examples of polynomial growth in commutative algebra or combinatorics. I'm sure you have many in your mind right now. But let me tell you a few from commutative algebra, since I'm kind of an outsider somehow in this crowd. So the first thing is we have the Hilbert-Samuel function. Okay, so if you have an imprimary ideal, then you can compute the length, which is the length of the composition series of the module, and this grows polynomially for n big enough. And this function here, this polynomial, leads to the very important invariant of Hilbert-Samuel multiplicity. Okay? You also have that the number of generators of the powers of an ideal grows polynomially. A little less trivial. So if you take the tors of certain powers, of the powers of an ideal, or the quotients of them, with respect to another module, then those lengths, also the lengths of x of a module with respect to R moduli to the n for certain ideal. You can, instead of taking length, you can take number of generators of Tor or X. All of these things are polynomial. Okay? And you can find all of this in a very nice paper by Kodayalam in 1993. Okay? The Castelnuovo-Montfort regularity. So this is a very popular object for us. Back in the year 2000, the same Kodayalam and independently Kotkowski, Herzog, and Schrung, they proved that the regularity of the powers of an ideal is eventually a linear function. Okay? So it's a linear on the nose. And since then, you know, we still keep studying this linear function because we don't understand, for instance, what is the the constant coefficient of it. Something more recent that I learned in a talk at Arizona State last week from Manohar, which is that there is this new invariant that people are studying called the V invariant. And that is, is the minimum degree of a witness of an associated prime of an ideal. And Konka, a couple of years ago, proved that that also behaves like a linear function. Okay? So you have a lot of polynomials here. But by the way, every result here is proven by using the Riesz algebra of the ideal. Okay? So this is the finiteness condition here. You put all the powers in an algebra, the algebra is Noetherian, and you exploit that finiteness to get predictable behavior, right? Now you can always replace the powers of the ideal by a graded family. Graded means that if you multiply the member In by Im, you get inside In plus m, as long as the Riesz algebra remains Noetherian. So if the Riesz algebra remains Noetherian, everything works, right? And the reason is because when you have a Noetherian algebra, instead of just standard graded generated in degree 1, you can find a Veronese that is a standard graded, and the whole algebra splits as a direct sum of certain modules. Now you can repeat the argument on each of those finally many modules, and you get those corresponding polynomials. So you get finally many polynomials that repeat periodically. Now, I'm going to talk about a related result that doesn't use Noetherianness, but it uses a different kind of finiteness. And this is in the context of local cohomology of monomial ideals. So if you've never seen local cohomology, let me quickly remind you what that is. If you have I, an ideal generated by certain elements, in this case, they are all monomial, then you can form the check complex. Okay? And the check complex is a complex that in the first degree, you are localizing at each of the elements in the generating set, and you take the direct sum. And then in the next step, you localize by products of two elements, and so on until you reach the end. Okay? And it is a non-trivial fact that the homology of these complexes don't depend on the generating set that you choose. I mean, the complex depends on it, but not the homology. Now, if you tensor the check complex by another module and take cohomology, those are the ith local cohomology, very well studied object in commutative algebra. Now, back in 2019, Hailong Dao and myself, we proved the following result. If the length of local cohomology of powers of an ideal, monomial ideal, is finite, then eventually they grow quasi-polynomial. Okay? And as I said, we don't use Noetherianness here. So let me, in the next few slides, tell you what we used to prove this. Yes?
Do you know the degree of the polynomial?
In this case, it's at most d. We don't even know if the constant, if the leading coefficient is constant, but it's at most d. Yeah, good question. So just a quick example. If you take the ideal x1, x2, x2, x3, x3, x4, x4, x5 in 5 variables, then the length of the first local cohomology equal this quasi-polynomial of period 2. Okay? And by the way, if you put this in a generating function, you get rational. Okay? And you're going to see later that this is not coincidence.
How do you see the period? Did you say this?
In this case, it's just, because there are two of them.
No, I know, but I mean, without seeing the answer.
I don't know.
Okay, so
no.
it's not a clear...
So no, we computed this. We computed this using the package normalis. Have you heard that? I've used it once and that's it. It was developed by Tim Rohner, Winfred Bruns, and other people that I don't remember the names, but it was very useful for us. But yes, I mean, we don't know what the period is. So we didn't use noetheriness. So what did we use? So the main ingredient is something called Presburger arithmetic. Okay, so let me spend a couple of slides telling you what that is, because I don't know if that's something well known. So a Presburger formula is a first-order formula, so from logic, that can be written using quantifiers, so that there exist for all, the Boolean operations, or, and negation, and you also have affine linear inequalities with variables. Okay? And the variables are going to be evaluated with integers. Now, we say that a subset of z to the d, is Presburger definable if there exists a Presburger formula that expresses membership in that set. So that means S is the set of all integer points in z to the d that satisfy the formula fu. Okay? Now, it is also a non-trivial fact proved by Kevin Woods in 2015 that this is equivalent to having finally many, a union of finally many sets of the following form. You take a sublattice of z to the d, you translate it, and intersect it with a polyhedron. Okay? So let me tell you a couple of examples. So the first example is you have the formula, this formula over here. So let me see if you're awake. What is this set?
All integers mod 1, 1 mod 3.
All integers, are you sure?
All positive.
Positive integers, okay, yes. So these are the positive integers congruent with 1 mod 3, right? Something less obvious, you can have this formula in two variables given by these two inequalities. And this defines the set of integer points in, you have it's like a cone that looks like this. Okay. And here is 1, 1. And the rays are given by these points over here, right? Another example that is very relevant for what is coming is the following. So suppose you want to find or express the monomials that belong to the nth power of a certain monomial ideal, okay? So if your monomial ideal is generated by x to the n1 to the x to the nu, so what you want is that your monomial, so the exponent of the monomial, is degree-wise bigger than or equal to a generator of the nth power. But the generators of the nth power is just a linear combination of the generators of the ideal that sum to n. So you can express that as there exist u variables, one for each generator, such that the sum of them is n, right? That expresses the nth power, and such that your vector A is component-wise bigger than or equal to this linear combination, right? So that expresses ideal membership in powers of ideal. But also, if you negate this, then you are saying that not belonging to an ideal or powers of an ideal is also Presburger definable. Any questions? I mean, if you have any questions, feel free to interrupt me. All right, so where do quasi-polynomials come in all of this? So they come because of this theorem by Kevin Woods. So if you have a Presburger formula in several variables plus another one n that I'm going to use as a placeholder, right? So what I'm going to count is how many points in z to the d satisfy the formula that you are given, right, with n fixed. Okay, for every n, you get a number, right, that counts how many a's there are. That's called a Presburger counting function. Right? And the theorem is the following. And this is a very impressive theorem, in my opinion. If I give you a function from n to n, the following are equivalent. First, you can find a Presburger formula somewhere that equals this function, okay, whose counting function equals this function. Second, the function or the sequence is a quasi-polynomial for n big enough. And third, the generating function of the sequence is a rational with the denominator of this form over here. Okay, so you have 1 minus z to the something, a product of those things. Okay? All of those things are equivalent. So let's revisit the example of this ideal membership. If you consider the formula now, these are the a's in n to the d, such that it is not true that the membership formula is satisfied. Okay? And let's consider the counting function. Why are you counting here? Well, because I'm negating, I'm counting the monomials do not belong to the power of I. So what I'm counting is standard monomials of r modulo I to the n. So this is just the length, right? Now, the conclusion is nice. It's quasi-polynomial, but we know in general this is a polynomial on the nose. So the proof is neater, but the conclusion is weaker.
And in this case, I is not necessarily a monomial idea.
No. So from this point on, almost everything I say is for I monomial. Yeah, because I need to have points.
I see.
So for Hilbert polynomials, we understand why it doesn't kick in right away. I mean, it's embedded points at the origin. Cohomology means it will kick in like error polynomials. Why doesn't it kick in here? What's the slogan?
Yeah, that's a good point. I mean, this is not a satisfying answer, but I mean, if you look at the generating function, you have a denominator that already tells you it's not gonna kick in from the beginning, depending on the degree of the
Although when
denominator.
you do the Hilbert polynomial in that form and you divide it out, you get a Laurent series, and then you get polynomial terms, and those polynomial terms are the errors in low degrees. But if it divides if it just stays negative powers, then it kicks in all the way.
You're right, and the short answer is I don't know. And I don't know if they know how to control those things. And that's one of the drawbacks of this theory, that you have the conclusion, it's quasi-polynomial, but what is the degree, when does it start, that you cannot control unless you dive into it. But if you're going to dive into it, you better just do something, something. But that's a very good question. Okay, so now that we have Wood's theorem, let me tell you a sketch of the proof of the theorem of myself and Dao. So there is a theorem called Hochster's theorem that you might have seen because it's very combinatorial, and it was revisited by Takayama to cover all monomial ideals. And this theorem says that the dimension of the degree A piece for a certain vector of local cohomology can be expressed as the dimension of the reduced homology of certain simplicial complex. Okay? And these simplicial complexes are not just any, they are subcomplexes of the Stanley Riesner? Is it right?
Riesner. That's what we decided. It's the most memorable thing.
I think it's the most used and memorable word in this conference.
Like the deceased piece.
Yeah, but well, so you have these complexes that are subcomplexes of a Stanley-Riesner complex. I'm not sure if I'm going to continue saying Riesner until I'm not sure. Yeah. Anyways, okay. Now, moreover, you can characterize the indices A for which, for a fixed complex, then the associated complex is equal to that one. And that equality is characterized by certain membership and non-membership of powers of monomial ideals. So maybe you see where this is going, right? Now, with this information here, let's prove the theorem. Okay, so let's say you want to compute the length of local cohomology, right? By definition, this is just the sum of all the dimensions as a vector space of all the degrees, right? By Hochster's formula or Takayama's formula, you can replace this by writing this finally many numbers, right? That's important. There are finally many, which is this dimensions of reduced homology. And now I can change the index of the sum by fixing the subcomplex and then gather all the indexes that give you the corresponding subcomplex. Here, you're going to have this number multiplied by how many indexes give you that complex. Okay? But Wood's theorem tells you this function here is quasi-polynomial. So you have a linear combination of finally many quasi-polynomials, so you get a quasi-polynomial. Right? Now, Kevin Woods and his co-authors, they have expanded this method. So if you're curious and interested and you think this might apply to your research, I encourage you to look at what they have done. And this is a survey article that he wrote. And I think the title is perfect, right? It's Unreasonable Ubiquitousness of Quasi-Polynomials. And in this article, for instance, they survey results that say, for instance, that in the linear inequalities of the Presburger formulas that you get, the coefficients don't even have to be constant. You can vary the coefficients by a parameter, and you still get quasi-polynomial. Right? So you have quasi-polynomials in many, many places that were not seen before. And people have used these things to prove quasi-polynomiality of certain information of numerical semi-group rings and so on and so forth. I mean, this is, I think, it has much more potential than what it has been used so far.
And does he use like the Erhard polynomial to prove all of this, or is
no? It doesn't use Erhard polynomial.
Some like first order logic type thing, or
in the end, everything is convex geometry.
Oh, okay.
Because the proof, if I understand correctly, the proof goes by eliminating quantifiers, and when you eliminate quantifiers, you have a bunch of inequalities. So he proved that the set that you want to describe is this truncating translations of lattices, and then you can argue in each of those things. But I mean, it's not trivial. Now, what is our goal, right? So after we came up with this proof, we had this idea that we have this finiteness condition, right? From local cohomology, expressing this the counting in terms of Presburger. But there was one problem, which is that everything relied on the Hochster formula that only applies for local cohomology. So if you want to prove for other functors or more complicated stuff, you need to find alternative things, okay? But something is clear from the proof, that if you want to generalize this to cover more stuff, then somehow your objects have to be divided into finally many pieces that can be described using Presburger. Right? Okay, so suppose you can effectively divide your object into finally many pieces and describe as Presburger. But if you want to do homological algebra there, you still need to have maps between those two objects. So let's say you have a Presburger definable object here, Presburger definable object here. How do you connect them? How do you map them so that you keep, things consistent? It wasn't clear for us. And this is one of the beautiful things of math. That is a very, there's a lot of serendipity, right? And there was this other group, especially led by Ezra Miller, that were developing methods to use commutative algebra techniques in multi-persistence homology. Okay? And yeah, this is the issue. And we read some of the stuff that they were doing, and everything seemed like this could connect, right? And Ezra wrote this very, very good article, and I also encourage you to read it. It's called Homological Algebra of Modules over Posets. Okay? And he develops homological algebra in a big generality, not just to like semigroup rings or anything, but just for any poset. And he develops resolutions, injective resolutions, everything like that. As I said, and the reason for doing in this generality is because he can apply it to multi-persistence homology, in topological data analysis. So after we found these papers, we sent a bunch of emails, and quickly we put together AIM square and trying to find if this serendipity was real. And now I can tell you that it was real. And the results that have come from these meetings is what I'm going to tell you today. Right? All right, so I need to introduce some terminology. Okay, so bear with me. Please don't get bored. Just interrupt me if you have questions and things like that. I promise this is going to get better at the end. Okay? But I need to tell you this for things to make sense, right? All right, so let Q be a free abelian group, right? And suppose you have inside a generating semigroup, right? So the group associated to the semigroup is Q, and you're going to put a poset structure to it. And what is the poset structure? 2 points in the group are related if and only if the difference lies in this Q plus, right? This is like the positive cone. Imagine you have a cone in the plane, and it's like going up, like a semigroup ring. Right? Now, a Q module is a K vector space graded by Q, so one vector space for each element in Q, and you have maps between related points in such a way that the compositions are well behaved, right? And you can think of this also as a functor from the category of posets to the category of vector spaces, for instance. For instance, this is the primal example for us. You have a fine semigroup ring, right? So this is a ring generated by a bunch of monomials inside the polynomial ring. If you prefer, you can think of this as the coordinate ring of an affine toric variety, right? And what are the maps here? The maps is what you expect, multiplication by elements in the ring, right? And everything behaves well, right? Everything is functorial. So for instance, once you look at it this way, then the ring itself, monomial ideals, quotients, everything are Q modules. Now, what is the finite condition that is going to do the job here? It's a condition called tameness, right? And let me explain what that is. So we say that a Q module is tame, and this is going to start looking right away as the Presburger thing I was describing before. A module is tame if the support can be divided in finally many, not finally many yet, but constant subdivisions. Finite is coming later. In such a way that for each subdivision of the partition, you have a fixed vector space MA, right? And the important thing is that you cannot have, you have no monodromy. What does that mean? That means that if you fix an A in one of the partitions and B in the other side of the partition, then the composition of the MA with this little a, B, and B, it is independent of which A you choose and which B you choose in the corresponding sets. So if you look at the picture, what we're saying is that it doesn't matter what point in this area you choose and what point in this area you choose. The map between them, right, is independent. It's like the same map on the nose, right? And the same thing here.
So is the choice of this partition, it comes with an isomorphism for each point as well? Like isomorphism from M capital A to MA?
Yeah, you have a fixed MA for each element of the partition. And isomorphism with each of the points.
Okay.
Yeah.
And that is part of the data.
Yes, that's part of the data. Yes, exactly. Yeah. Now, we say that the module is tame if the division is finite and each vector space in the module has finite dimension as a vector space, right? Moreover, we say that M is a Presburger module if the constant regions can be described using Presburger. Right? So remember, Presburger implies you have some linearity. So this division would be Presburger if the boundaries are linear. All right, now I need to introduce Presburger families. Now, we want to imitate what happens with the Riesz algebra. So we consider the Presburger Riesz monoid. What is that? So you're going to extend the dimension of your group by 1, right? And you're going to say that G plus, right, the G plus of the extension is a Presburger Riesz monoid if the intersection with the base is the positive cone of the base. So for instance, what I'm saying here is that if this is Q plus, then G plus is here, right? So the intersection of the positive cone in one dimension more with the lower dimension gives you exactly the positive cone over here. Right? And we say that a family of Q modules is a Presburger family if the direct sum of them forms a Presburger module with respect to the bigger group. So for example, the following are families of Q modules. You have powers of monomial ideals. You have integral closures of monomial ideals, symbolic powers, saturations with respect to another monomial ideal. However, these are not the most interesting examples because they are all Noetherian graded families. Yes?
So they're Presburger because this monomial condition is essential, because you're looking in the multi-grading and you're partitioning every entry, every vector space is 0 or 1, basically?
No, they don't have to be 0, 1. They only have to be finite. But the important thing about Presburger is that your subdivision is expressed in terms of Presburger.
Yes. But I mean, if I just took powers of ideal in a standard grading, and I looked at the graded pieces, they wouldn't be Presburger at all, because the dimensions. So monomial is crucial because it enables you to subdivide into regions of constant vector space dimension.
It has to be Q graded, right?
Okay.
So it has to be, let's say, n to the d graded, right, ideal in the polynomial ring. So everything is monomial. Yeah.
Thank you.
John?
Yes?
Fast one more.
Yes.
Getting a little lost in the notation.
Okay.
So I'm thinking about Q as being z to the n, where Q plus is the lattice points in a pointed cone.
Yes, exactly.
That's a reasonable way to think about it.
Yes.
And so then what I'm doing then is I'm thinking about, so G is isomorphic to then z to the n plus 1.
Correct.
And so then I have like a sublattice. So then I take z to the n plus z, and I'm thinking about that as like extending the cone in that extra dimension.
Correct.
And then I'm taking a sublattice of z to the n plus 1, and essentially saying that G plus is the stuff that's contained in that extended cone.
Correct.
But I actually need to make sure that sublattice contains everything in the original cone that I started with.
Correct, yes.
Okay. And is that always the picture? Is it always this geometric picture, or are there other groups?
That's the picture that...
That's the one that matters.
That's the one that matters, yes. Okay. So if you want to think about it, consider a monomial ideal in a polynomial ring and take the Riesz algebra.
Yeah.
So if you consider the Riesz algebra, then everything is multigraded in one dimension more. Now take the monomials in that dimension more. That's the picture we're looking at. So the ring is the base, and the Riesz algebra is the cone in one dimension more because you're adding this extra variable.
Thank you.
Okay. Any other question? Yes.
You told us to ask questions.
Yeah, please. I don't have to get to the end, yeah.
Just following up on Dan's question. So if I take an ideal that is not monomial, I could create a Q module by taking the powers of the ideal. So I grade it by just, if it's homogeneous, let's say it's a homogeneous ideal, then it's going to be Q graded by the integers, right, by the natural. But it wouldn't be Presburger because the vector spaces don't stabilize. They're not finite, but they change at every point.
So the point is that if you consider a Q-graded ideal in the semi-group ring, then that's monomial.
So if Q is just one copy of the natural numbers,
Yes.
then a homogeneous ideal is just set-graded, right? N-graded.
But the ring that we're looking at is adding one variable only in that case. Because the ring would be, I mean, if you're considering Q to be, Q plus to be N to the D, then the ring in that case would be K N to the D, which is the polynomial ring in the variables. So
I see. So Q is already telling you what the bigger ring with everything is.
exactly, yes. So everything is, yeah. Once you go outside the monomial case, we don't have a theory yet. Hopefully, it's in the progress, but All right, so more examples. So if you consider columns of linear powers of an idea with respect to another idea, this is not even a graded family, but it's Presburger. Now, maybe you have seen these multiplier ideals that geometrically are defined by taking resolution of singularities. But for monomial ideals, they are expressed in terms of the Newton polyhedron that Michael was describing earlier today. So multiplier ideals of powers also form a Presburger family. In fact, it only suffices that the intersection of the columns of one member of the family of ideas with respect to the previous one, that the intersection of all of those have at least one non-zero element. And if the membership in the sequence is Presburger, that already implies the family is Presburger. So for instance, if you start with a Presburger family, you can take integral closure of those, you can take columns, you can take saturations, even multiplier ideals, and it remains Presburger. So you can combine all of this together and get complicated stuff like, suppose you take the columns I to the n, j to the rn minus 2, take the multiplier ideal, saturate it with respect to k, and take the closure. That's still a Presburger. And because they are closed under direct sums and quotients, then you can put them together and create more complicated modules, right? So these are all describable in this category. All right, so what about the maps? All right, so a homomorphism of Q modules is a bunch of maps for each degree such that these squares are commutative. And we say it is tame if it respects the subdivision, right? So that means for each part or partition of the division, you're going to have that the map from this fixed vector space to a member of the subdivision to the other map, and the other one, this doesn't depend on the element that you take in its division. And if the partition is Presburger definable, then we say the map is Presburger. Now, this is where the homological algebra starts to get all together. So Miller, in this paper that I put before, he proved that if you take kernels or co-kernels of tame morphisms, then it is again tame. And he, moreover, proved that if the subdivision satisfies certain properties, then that property is preserved by taking kernels and co-kernels. And it turns out that Presburger lies into those conditions that he put over there. Right? So Presburger is respected by kernels and co-kernels. That means that if I create a complex of Presburger objects, so you have Presburger modules, Presburger maps, and you take homology, that's still Presburger. Right? Any questions so far? All right, so he even proved some resolutions, right? So we say that a module, or a subset of Q, of the support, is an upset if it is closed under going up, right? And he calls the indicator module of an upset module. And he proved that, and this is coming now, but he proved that every tame module has finite upset resolution, meaning that you can create a complex that has finally many degrees, and each degree has finally many upsets as a direct sum, and keeping everything exact. Right? So for instance, you can see here the start of a resolution. Let's say you want to have an upset presentation or upset resolution of this object over here. You can see this one as a co-kernel of this map over here. Right? So if you map this upset to this upset, the co-kernel kills everything that belongs here, and this is an upset presentation. Right? All right, now let's talk about our theorem. Right? So the data here is let Q be isomorphic to CC to the D, so you have this free abelian group with a generating sum group as the one I described before. Now the theorem is that if you start with a Presburger family, then the following are Gerd Presburger. First, you can localize at a monomial prime. Now if you have seen this before, the monomial primes of a semigroup ring are correspond to the facets of the cone. So it's like you're going in the negative direction of one of those facets, of one of those faces. Sorry. You can take local cohomology with respect to any monomial ideal. So before we had argued that there was a way to do it, we support in the maximal ideal. Now we can take any support monomial. We can take torus with respect to a Noetherian R module. You can take X and X on the other side. Right? And for the one on the other side, it is important that you have finally many Bass numbers. So you need Noetherian or Artinian modules.
You don't need the L's or whatever to be Presburger to satisfy some additional constraint too? So grading is enough.
Presburger is more general than Noetherian. So if you have something Presburger, it doesn't have to be finally generated. But for this, we do need Noetherian. So yeah. And I have a sketch of the proof for the Tor, and that I explain why we need Noetherian here. So for example, you can create complicated looking Presburger families. For instance, you can take local cohomology of powers of an ideal. You can take X and then take X and take X, X, X as many times as you want, and that's still Presburger. You can create your favorite Presburger module and then compute the Betti numbers of them. Remember, the Betti numbers are computed by considered Tor with respect to the field. And also Bass numbers, because Bass numbers are the X from R modulo P a prime, and then you have to localize. So let me tell you a word about the proof for the Tor, and here I tell you why we need Noetherian. So if you tensor a free resolution of L, remember L is assumed to be Noetherian, so the F is a free resolution with an upset presentation of M. Right? Remember, if you have Presburger, you have, by Miller's theorem, you have this resolution by upsets. So the Z's is a presentation of upsets and the F's are free. So they're direct sum of copies of the ring. Now, the co-kernel is what you want, because tensor product is right exact. But the point is that in this square over here, you're going to have the composition into several direct sums. Remember, the frees are just direct sums of free, and the z's are direct sums of upsets. So everybody here decomposes as a direct sum of a tensor product of an upset with a free. But the free are like a point and going up with respect to Q plus. And it turns out that there is a Presburger nice way to describe these maps over here. Namely, they are 0 if this condition is not satisfied and it's multiplication by an element in K otherwise. Okay? And now the proof ends by just taking homology. Now, tensor products of general Presburger upsets need not be tame, and that's why we need L to be Noetherian. So for instance, consider the following upset. So you have here the plane, and here L, and consider this upset. If you consider the tensor product of this upset with itself, then at this point over here, you're going to have, at the multi-degree corresponding to this point, you're going to have an infinite dimensional vector space, because symmetric points in this line add up to this point. So it's not even tame. However, if you are tensoring something that looks like this with something that looks like this, that doesn't happen. Right? So that's why you need Noetherian here. Any questions?
Of course, that's infinitely generated as a monomial ideal. I think there's a real monomial ideal that has infinitely many corners.
But the point is that you don't need finite generation here. Yeah. The finiteness come from finitely many regions that you can describe with Presburger. But as long as one of them is like this, then it's fine. Okay, so what about the quasi-polynomials? Right? I started with the motivation of finding quasi-polynomials everywhere. So in these last 2 slides, let me tell you some things that we prove are quasi-polynomial. Okay, so if you begin with a Presburger family, then the following are quasi-polynomial. The lengths of local cohomologies. Now, this length may not be finite because local cohomology is not Noetherian. But all you have to do is truncate the support with linear functions. And now you have a Presburger Noetherian object, and the length is quasi-polynomial. For instance, things like this, that there were no way to prove this before, right? You can take local cohomology with respect to 2 variables in 4 variables, with respect to a sequence that looks like this, and then as long as you truncate the support with linear functions, everything is quasi-polynomial. Now you also have lengths of torus and x, and I'm kind of cheating here because you have to truncate the support, because if you start with something that doesn't produce Noetherian, you have to truncate it, but still. You can replace lengths in this by minimal number of generators, and everything is fine. You can take Betti numbers, because those are dimensions of torus. You can take Bass numbers, because those are dimensions of this localization of x. A invariance. The A invariance of a module is the maximum degree where local cohomology with respect to the maximal ideal doesn't vanish. Okay? Now, you can start with any of those Presburger sequences, and the A invariance still quasi-linear. The regularities of all of these guys are also quasi-linear. So, for instance, I just put this example as a reference. This is a complicated example that I produced in one of the slides. I mean, there was no way to prove that something like this was linear before. Now, this new invariant that people are studying, the D invariant, not only is linear for powers, now it's linear for any Presburger sequence. Multiplicities or degrees. These are also now polynomials. Okay. And there is a more general notion of degree by Vasconcelos introduced in 1998 called the homological degrees. And those degrees are linear combinations of finally many degrees of modules that look like x, 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 x. That's why I put that example before. Okay? But I know those degrees are quasi-polynomial. So you put them together, you get a quasi-polynomial. By the way, before this, it wasn't even known that the homological degrees of powers was polynomial. Right. Thank you.